Well, hello everyone, and welcome back. I'm Jack Rincon here with Dr. Pepe Ping, and we're pleased to continue our Bridge to AI TRM Working Group lecture series for 2025 to 2026. We're excited to share another cutting edge session with the consortium community, the Bridge to AI Consortium, Encrypted Machine Learning. Dr. Ping?
Uh, Thank you, Jack. It's truly our great honor to welcome today's speaker, Dr. Vishnu Boddeti. He is Associate Professor in the Department of Computer Science and Engineering at Michigan State University, and he's also the Director of the Human Analysis Lab. Encrypted machine learning is a fascinating area of development with great potential to transform AI in the healthcare domain. We are honored to have him to join us, tell us what his focus of investigations are, and the amazing outcomes that he's looking at. Let me do a little bit introduction about Dr. Boddeti. He's currently considered a world leader at the intersection of trustworthy AI, cryptography, and machine learning. At the Michigan State University, he directs the Human Analysis Lab, where his work focuses on building AI systems that come with provable guarantees of fairness, privacy, and reliability in high-stakes domains such as clinical data sets. His research spans bias auditing in foundation models, adversary testing of AI systems, and the development of cryptographically secured learning methods. All of that based on homomorphic encryption and FHE native architects. Dr. Boddeti has received multiple prestigious honors in recognition of his accomplishment, including the 2024 IEEE CCF Cloud Computing Best Paper Award and another Best Paper Award at IROS, as well as at IEEE TBIOM. The recognition continues as he has been selected by the editor in Nature Communications as editor highlight. Recently, he also serves in key leadership roles in the AI trustworthy community, including senior area editor for IEEE transactions on information forensics and security area, as well as area chair for the neuro-symbolic. We are so fortunate to have him guiding today's lecture and giving us discussions regarding the topic of patient privacy preserving machine learning. Back to you, Jack.
Thank you, Pepe. So in today's session, we'll focus on three key learning objectives. First, we'll explore how encrypted machine learning can enable privacy-preserving analysis of biomedical data while still meeting the stringent regulatory and strict requirements that govern clinical and research environments. This is especially critical as institutions seek to collaborate across sites without exposing sensitive patient information. Second, we'll gain an introduction to the core cryptographic ideas that make encryption computation possible, including the principles behind homomorphic encryption and how they reshape what is feasible in secure AI systems. And finally, we'll examine the real-world challenges of deploying encryption, machine learning, in biomedical settings, including computational costs, scalability, and integration with existing workflows, and consider how these barriers might be overcome. These perspectives will help us think more rigorously about how security, privacy, and performance can coexist in next-generation biomedical AI and healthcare. With that, I'll hand it over to Dr. Boddeti to take us deeper into the topic. Please share your
Right.
screen.
Thank you. Thank you, Jack. Thank you, Pepe. So I'll start sharing my screen here. Oops. Sorry. So please let me know if you can see the full screen.
Yep, you're all good.
Okay. Very good. Thank you very much. So this is going to be a discussion on encrypted machine learning. So there has been a proliferation of AI in our lives. So we see them very regularly. In fact, most of you probably already use them, especially chatbots, or if you're driving a Tesla vehicle, then you have this self-driving systems. They're also being applied in healthcare scenarios for improving stroke diagnosis, faster diagnosis, MRI, CT scan analysis, and things like that. And of course, going into the future, we're going to be looking at maybe humanoid robots. And there are some very interesting ones already coming out in the market. So basically, we all have been exposed and we all use AI systems a lot these days. But let's actually take a step back and look at what's the state of affairs of these AI systems. So they're very good. They work very well. We all know that. But what are the downsides? So first, looking at this from an academic world. So there have been documentations of many types of attacks on these kind of AI systems. So I'll showcase a few of them here. So one is attacks on face recognition systems. So face recognition systems are widely used every time you use your iPhone or your Android phone, or even if you go to the airport and you want to catch a flight and things like that, your face and fingerprints or biometrics are being used to identify who you are. But there are attacks that are possible on these systems, and these have been demonstrated. So your face template that is stored in a database, you can actually recover your full face image from just these templates, and then you can actually attack these face recognition systems either by simply printing a photograph or by replaying it on a phone. So here's an example. This is a printed photograph, and that is enough to just unlock your iPhone. Same thing, just a photo on a screen. Again, it's enough to unlock your phone over here. So this is one example of an attack that's feasible and has been demonstrated. There are also lots of attacks on large language models, which are very widely used nowadays. I'll just highlight a few of them here. So these attacks, you can, from the embeddings of this text data, you can actually recover pretty much the original text. So these models, you typically store embeddings, but from these embeddings, they are believed to not contain all the private information, but this attack shows that you can recover pretty much the whole text, original text. You can go much further than that. It's not just revealing text from the embeddings. You can actually invert the model itself. So just from the outputs of this large language model, you can basically find an inverse of this language model and reconstruct what was the original text or the prompt that was actually entered into the system. You can also extract the prompts itself that people enter just by looking at the outputs. So even if you just look at the outputs of this large language model, let's say a ChatGPT model, you can actually figure out what was the question or what was the prompt that the user entered. So these are all serious privacy challenges, demonstrations of attacks in the academic settings. Now, let's see a slightly different setup. So what is the state of affairs from the real world in terms of breaches and attacks? Here's one from the news media. This was in 2024. This is from Australia. There's a medical lab in Australia that is training their AI system on users' data, user scans like these. But this company has never actually asked the users for their permission to use this kind of data. So that's a privacy issue right there. The people did not even know that the data was being used. And here's some statistics on the number of healthcare data breaches that are happening over the past, let's say, 15 years. So, of course, in the beginning, there were very, very few, maybe 18 or maybe 200 in the 2010s. And this is from 2025, we are up to 710. And I think this is only going to grow much, much higher with all the chatbots that people are now using. So I expect this graph to keep going up exponentially. So what's the summary of this, right? So we all know AI systems are very effective and we use them, we love them, but they also suffer from privacy and security vulnerabilities. And we need to address these privacy and security vulnerabilities if we want to use these AI systems in high stakes applications, let's say like healthcare, education, finance, and things like that. So of course, in healthcare, there are strict privacy requirements, through the HIPAA. So you have to follow these privacy requirements. It basically says that you need privacy while the data is being transmitted, while it's being stored, and also while it's being used. So this kind of strict regulations prevent you from very freely sharing medical data, very freely using, let's say, cloud services with medical data without violating patients' privacy. So there are many different privacy enhancing technologies. So there's a few of them that you may have heard. In fact, differential privacy is very popular. This was even used in the US Census, the last US Census, to anonymize user data. There's secure multi-party computation, there's homomorphic encryption, and trusted execution environments. So there's a lot of different types of privacy enhancing technologies. Each of them have their own advantages and disadvantages. For example, trusted execution environment, you need a very special hardware, special chip on your phone or your computer. Without that, this is not possible. With multi-party computation, you need many users to interact with each other, which may not always be possible in the real world. So our agenda is going to be today to see how we can leverage encryption for AI systems in order to enhance the privacy and security of this user data. But before we get into the details of this, let's actually take a step back and see what are we really trying to protect in healthcare. So this is a simplified picture of an AI system, right? So you have some data that's going into the system. So this is my big AI model, and I'm getting some output over here. So the input in the healthcare context could be, let's say, a medical image or electronic health records, genomics, your voice, your identity, lots of different things. And the model over here could be some AI model parameters that is specifically designed for healthcare applications or some diagnostic algorithms. So there are two kinds of privacy requirements here. First one is data privacy. This is very widely known in the healthcare community. You want to be able to protect your input data. So this could be patient information. You also want to be able to protect the output, the outcome of this, whatever prediction this AI system is doing. So you want to protect both in order to protect the data privacy of the user. A slightly maybe less known privacy requirement is this model privacy, where let's say I'm a startup and I designed a proprietary model for doing healthcare analysis. Now, I don't have the resources for deploying this model, so I will maybe deploy it on the Amazon cloud or a Google cloud or some other external cloud service provider. Now, when I do that as a model provider, how do I ensure that my proprietary information in this model is protected? As we saw earlier, it is possible to even recover the whole language model parameters just from looking at inputs and outputs. So as a company with using patient data for training this model, I want to be able to protect this. And this is called model privacy. It's not very widely discussed, but I think this is also a very important aspect of privacy, especially in healthcare context where people are designing custom models. So you might be wondering, okay, there are many encryption algorithms, right? Traditional encryption algorithms in computer science, it's an old topic. People have been maybe studying encryption for maybe more than 100 years. So why can't we just take those encryption algorithms and just use it? So here's the reason why. So what are traditional encryption algorithms good at? So let's consider the scenario. Let's say I'm the user, I'm sitting on my computer or on my phone, and here's a server. Let's say this is Google or Amazon, and I'm going to send data over from my device to this server over, let's say, Wi-Fi or my cellular network or even a hardwired network. So what current encryption algorithms do is they can protect the data. You can encrypt it on the device. They can protect the data while it's being transmitted to the server. And as the server, while it is being stored, also it can be protected. But however, the moment you have to do a computation on this data on the server, what you do is you actually decrypt the data. So you have to decrypt the data. So now the data is all public or exposed. And then you do your computation. Let's say you're running some neural network on this data and or AI model on this data and getting some computational output. Then you take the output, you re-encrypt it, and then transmit it back to the user. So the problem here is that this server over here can actually see what your data is. They can violate the user's privacy if they want to, if the server is malicious. So in short, the privacy of the user is not guaranteed in this type of traditional encryption algorithms. So if you just think about this, what we have in encryption system, the current encryption systems, is we can protect data when it is stored at rest on a computer. We can protect data while it's being transmitted to between the client and the server. But we cannot protect the data while it's being used for computations, while it's being, let's say, used to make predictions through an AI model. What we ideally want is we also want the data to be protected while it is being used as well. So we want to protect the data at all the time. It's when it's storage, when it's transmitted, and also while you're doing computations on the data. So the natural question is there an encryption scheme that satisfies this, whatever we desire? We desire encryption always. So such an encryption scheme exists. It's not a single scheme. It's actually a family of schemes. And this is called fully homomorphic encryption, or FHE. That's the short form for fully homomorphic encryption. So what does it do? It basically protects the data on the server while it's being transmitted, and also during computation. During computation, you actually decrypt. There's no decryption, re-encryption box here. Everything happens on the encrypted data itself. So this enables AI models to process encrypted data without decryption. So that gives you end-to-end privacy. So from here, all the way, all the computations, everything happens encrypted. Another nice property of this fully homomorphic encryption schemes is that they are conjectured to be post-quantum secure. That means even if we get more powerful computers, let's say quantum computers in the next 20, 30, 50 years, these encryption algorithms are secure even against those more powerful computers. So this is a very nice class of encryption schemes that we can leverage for AI models. Right. So just a formal description of what fully homomorphic encryption is, you can run programs on encrypted data without decrypting it. In fact, you can, in theory, you can do any computation on it. People do lots of crazy things with encryption, fully homomorphic encryption. Someone built a whole game of Conway's game of life on it. Someone also simulated an entire microprocessor entirely on encryption. And if you have actually used an iPhone, and if you use photo search, your iPhone is actually using homomorphic encryption to protect your photos. So they do search over encrypted photos. And if you ever used Microsoft's Edge browser, they also use homomorphic encryption for password search. So this is to ensure when you, let's say, type a password, they'll search and tell you if it's a widely used password or not, or if it's a safe password or not. That search is actually done over encrypted passwords. So again, the browser itself is running this homomorphic encryption for you. So what we'll do here is we'll look at some foundational concepts of homomorphic encryption, and we'll look at how we can leverage homomorphic encryption for neural networks, and I'll show you some applications. All right, let's start with the foundational concepts here. So the idea of homomorphic encryption is not very new, actually. People have known about homomorphic encryption way back in 1978, okay, almost 50 years ago. But it was not very useful at that point. There are some limitations with the idea that was presented in 1978 until the breakthrough by Craig Gentry, who was a PhD student at Stanford in 2009. So he proposed a homomorphic encryption scheme that basically allowed you to do any computation on encrypted data. So this was really a breakthrough result that basically makes encrypted computations feasible. Since then, of course, there are many different encrypted computation FHE schemes that have been proposed. The most relevant one that we will be using is called CKKS, named after the authors who proposed this in 2017. And CKKS is the one that is most relevant and useful for AI models because it allows computations on floating point real number data, which is what we use in AI models. So a lot of the discussion I will have is about CKKS in the next few slides. Right. So what is the core principle that makes homomorphic encryption so secure? Okay. So this is called the learning with errors problem, or LWE for short, and people have studied this for a long time. So let me try to illustrate what is this learning with errors and what makes this really secure. So let's say I have a secret key and I have a public key. So this is a public key encryption system. That means you have two types of keys, secret and private and public. And the goal of any attacker is going to be, or if you want to break the FHE system, your goal is given this public key or this set of equations, I should recover this secret over here. Okay, so this secret is basically these numbers, W, X, Y, Z, and so on. Okay, so those are the four numbers that we do not know here, but we want to recover this. So if these numbers are all real valued, okay, so that means these are floating point numbers, then given this equation, we know how to recover these W, X, Y, and Z values. This is simply solving a system of linear equations. This is done in linear algebra. We have very efficient algorithms to do this. So this is not secure, basically. So let's start making it more complex so that we get to the stage where it becomes really secure, in fact, quantum secure. So now let's say we add some noise to these values. So that makes the problem a little harder. But you can still somehow solve for this. This is called the least squares estimator or the least squares problem. And this, again, very widely used. Everyone uses this. We have very good algorithms to solve this problem. So far, this is still not secure. Okay, so this is just linear equations, and we know how to solve them. So now we will add one small twist to this. We will say that these numbers are not real valued numbers, but they actually follow a ring structure. That means these numbers repeat after a particular value. For example, in this example here, the numbers are going to be 0 to 89. And after 89, I don't go to 90, I go back to 0. That's what this means, this modulo operation. That's it. This simple trick now makes this problem quantum secure. It makes it really, really hard. We have no solution to solve this problem, even with very, very efficient or very, very powerful computers. Okay, so this is basically the underlying theory of how or why this encryption scheme is very, very powerful. And if you want to use this encryption scheme, there are a lot of different operations. There's an encoding, decoding, there's encryption, decryption. You have to generate keys, you have to evaluate. So this is the whole pipeline of operations or sequence of operations that happen over here. So I'll just maybe quickly go through some of these and skip a few. without going to too many details here. So the first thing is you want to encode this information. So if I have numbers, I have to encode this into what are known as these polynomial rings. And now I can do this encryption on top of these polynomial rings. And then I can also I need to also generate these keys, the secret key, public key, and a special key known as an evaluation key that I need in order to do computations on encrypted data. And you have to be careful about how you select these parameters for these encryption keys. Only in some region they are secure. If you choose the wrong set of parameters, your system is not going to be secure. So you have to be careful about how you choose these. And then once you have these keys, you can do encryption and decryption. This encryption and decryption operation is very simple in terms of polynomials out here. But one idea behind this encrypted data is what are known as multiplicative depth or levels. Think of this as a battery. So every encrypted data is, when you start off, it's a full battery. Okay, so you have a lot of energy and you can start doing computations. When the battery is depleted, then you can no longer do computations. So you're stuck. So I'll get back to that battery aspect in just a second. So now let's say I want to do some computations on this encrypted data. I can actually do a couple of different computations. I can add numbers, simple addition, let's say 3 plus 5, or I can multiply numbers. So those are the two operations that I can do. I can only add and I can only multiply numbers. I cannot do other operations on this encrypted data. And one special aspect about this encryption schemes is that typically multiplication is much, much slower than addition. I can add numbers very quickly, but multiplication is really, really slow. This is not the case in normal standard computation. In normal standard computation, addition and multiplication are typically equally fast in today's computers. But that's not the case in encrypted domain. So now let's get back to this battery concept. So let's say I have a encrypted set of numbers. And when I start off, I have a lot of energy. I have full energy. My battery is full. But now I do one computation. Let's say I do a multiplication. I multiply this set of numbers with this set of numbers. Each multiplication depletes my battery by a little bit. So maybe I lose a little bit here. I do one more computation. I deplete my battery a little bit more. I do one more. I deplete it more. Do one more. Now I'm basically exhausted. I have no more battery left, which means that I cannot do any more multiplications or any more computations on top of this. The computations will no longer be correct if I continue doing this. So in order to actually continue, what we need is something called a bootstrapping operations. You can think of this as charging your battery again. So you can run this bootstrapping operation, and now your battery is full again. And now I can continue doing more computations on this. So this bootstrapping idea is very important if you want to apply this for neural networks or AI systems, because AI systems are essentially a sequence of lot of multiplications, even probably in the thousands of multiplications. So you frequently need to do this bootstrapping in order to continue doing these operations. But one aspect of this bootstrapping is that it's very, very slow. So your goal is to try to avoid it as much as possible because it's really, really slow. So that's basically what's going to be the key idea for making these AI systems efficient under encryption, by trying to avoid as many bootstrapping operations as possible. So we can also do some packing of the data. You want to encrypt a whole vector of numbers, because in AI systems or in machine learning, we operate with vectors of numbers. We don't operate with scalars. So you want to do some packing. And there's different ways in which you can do this packing of numbers. And how you do this packing affects how efficient you are. If you do it correctly, then you're going to be super efficient. If you do it incorrectly for your problem, it can be very, very slow. So you can do a whole bunch of operations with just additions and multiplications. You can do vector operations. You can add vectors, multiply vectors. You can rotate vectors. But each of these computations are not equally fast. So rotations are very slow. Multiplications are a little faster, and additions are much faster than multiplications. You can do polynomial evaluation. This is what is necessary in AI models. In AI models, you have all sorts of nonlinear operations like sigmoid activation, ReLU activation, JLU activation, and softmax. So all of these are nonlinear functions. You need to approximate them through polynomials. And you also need a lot of matrix operations in AI systems. For example, neural networks have linear layers or attention layers. These are all basically matrix operations. So you have to be able to do these type of matrix operations over encrypted vectors. So if you're working with transformers, you have all these matrix multiplications that you have to do. And transformers are basically the underlying architecture for large language models and even image generative models these days. So far, what we have seen is that the basics of encrypted computations, you can do additions and multiplications, and there are a couple of things that you need to be mindful of. One is how you pack your data. You have to be mindful of bootstrapping, which is this battery that you need to keep recharging if you want to continue using this encryption. And also the fact that different operations have different computational speeds. So now we'll try to see how we can take these concepts and apply them to AI systems or bigger AI models. So first, before we start looking at those solutions, let's see what are the challenges of directly applying this FHE to AI. So these are four different challenges that I listed here. One is these libraries or these software packages for encryption are very low level and they're not user friendly. So you need to have high skill in terms of encryption and software libraries in order to use them. These are typically written in C++ or GPU CUDA, which are not user friendly. Secondly, they are very, very computationally expensive. So this homomorphic encryption is almost 10,000 times slower than regular computation. So this makes everything very, very slow. So you have to try to speed this up. It also doesn't support many AI model layers like nonlinear layers. And typically, using these systems needs expertise in both cryptography and AI, both. And this is a very, very rare combination, a rare set of skills. So it's very hard for one person or one set of people to have these skills. But these are the challenges, and people are now making progress on addressing these challenges, some from our group and some from other groups across the world. So essentially, there's libraries that are now trying to make these, to mitigate these challenges and make these systems more user-friendly and more performant. So I'm going to discuss some of these now. So first is how to make this user-friendly. So by user-friendly, maybe as an AI systems engineer, you are probably very familiar with PyTorch, where you can write your neural network definition, you can train your model, you can run inference, you can do all this. This is very, very widely used by AI engineers these days. So what you want is something that looks like PyTorch, and with minimal changes to the code, you should be able to run encrypted computations on this neural network. So Orion is a library that actually does this. And I have a small snippet of code over here, which shows you how easy it is to do encrypted computations now. So essentially, you add 4 lines. So these are the highlighted lines. So you say import Orion in Python. You define your neural network in regular PyTorch. And then you call these 3 separate lines. And that's it. You add these 4 pieces of lines, and now your neural network becomes encrypted neural network. So it does all the computations encrypted. All the magic happens, in the back end. So you don't have to sit and work with all the low-level code. So this makes it really, really easy and user-friendly to start doing encrypted computations with neural networks. So that's on the library side of things. So we're also trying to change the AI models itself so that they are more compatible for FHE computation. So this is how to adapt these models for encrypted computation. So let's say I have a neural network. It takes an image and it takes a neural network, which is essentially a convolutional neural network here, and I get some output. Our goal is to encrypt the data over here and do all the computations in encrypted domain and get an encrypted prediction at the end for privacy. So encryption can support multiplications and additions and rotations. Those are all the linear layers and so on. But all these non-linear operations like ReLU, they are not supported by encryption. So you cannot do these computations on encrypted data. So this is where you actually need to do some approximations through polynomials so that you can do this computations over here. So this is one type of adaptation. So you take your neural network and you look at all the nonlinear layers like ReLU and you change them to polynomials. So this polynomial activations, you can do different levels of approximation. You can do very high degree or low degree approximation. So you can do a simple approximation or a very, very good approximation. Both of these basically lead to a trade-off. You're either very fast and very weak approximation, or you're very slow, but you're a very good approximation. So this is a trade-off that you actually need to pay. Overall, designing this encrypted AI systems needs, designing the neural network aspects of things. This is what a standard AI researcher would do. You would go and define all this architecture with different layers and things like that. But now you also need to consider all these encryption parameters and stuff. Now, what you need to do in order to make this fast, efficient, and secure is you need to co-design them. You need to do this together. You cannot just do one thing and leave the other. So people have tried to use low-degree polynomials, high-degree polynomials, and we came up with a method that can actually do mixed-degree polynomials, which will trade off between accuracy and latency. So you can do this with manually designed. This is from a couple of years ago. This is a very complex neural network with encryption modules in between over here. And these are all manually done, hand designed, very painstaking. But instead, we actually came up with an automated algorithm so that you can make this more user-friendly and more scalable. So this automated algorithm, you don't need to do this by hand. It will actually search for the things of what type of approximation should I do? Where should I place these bootstrapping operations? And you pose it as a search algorithm, and you can basically get a very flexible neural network architecture, and you can do on-demand bootstrapping. Bootstrapping is something you want to avoid as much as possible. So you can do this for a standard image classification. So this is an example on CFAR10 dataset. You can do encrypted end-to-end classification on these images. You can also do this on bigger datasets like ImageNet as well. So here's some results on what happens when you try to do this with manually hand-designed, painstakingly hand-designed neural networks for encryption versus the automated algorithm for encrypted neural networks. So the first one here is from 2022. They do a manual design of this, and they get a pretty good performance here. And this is the x-axis is the latency, or how long it takes to do this inference. As you can see, it's pretty slow. So for each image, classifying each image, you take around 90 seconds per image. That's a lot of time. In a regular computation, this would happen maybe in less than a second. But with encrypted computation, this is going to be 90 times slower. It's going to take 90 seconds to do it. But if you start maybe trying to do more But if you actually do use this automated approach that we proposed over here, which is called AutoFHE, you can improve that by a factor of 2. So instead of maybe 90 seconds, you're now down to 40 seconds. So this is on a CPU. And more recently, you can do this. We showed how to do this on a GPU, and that can bring this from 40 seconds down to 4 seconds. So it is still about 4 times slower than regular computations. But now it's in the space of, okay, I can actually start using this for some high stakes applications where speed, computational speed is not maybe a focus. So you can go beyond simple image classification. You can do end-to-end encrypted face recognition. In face recognition, you can encrypt your face right on your phone. You send it off to, let's say, Amazon's face recognition system or Google's face recognition system. Completely encrypted. You do everything encrypted over there through the neural network and also the face matching. And you get the claimed result back encrypted as well. So this is really makes the whole thing really secure end-to-end, both at the image and also the database of faces. So in order to do this, we had to do a few more things because face images, you need very high resolution images, and encryption doesn't support very high resolution right now. So we had to come up with this idea of breaking an image into patches and processing these patches in parallel. So this way, your neural network is fast. You can parallelize it and still process high resolution images. So this was recently shown actually in 2025 by our group. And we showed that you can do this really efficiently, really quickly. So if you use a standard neural network like a ResNet, this is going to be really slow, about 1200 to 1600 seconds to match one pair of images. That's really slow. With our automated design technique, you can bring this down to maybe 600 seconds to match a pair of images. But with our custom design of CryptoFace, you can actually bring this down to 220 seconds. So this is about an 8-time speed up over a standard neural network. So a lot of methods that use neural networks with encryption, they try to put encryption on top of standard neural networks, but that doesn't take advantage of all the computational speed up that you can get by custom designing these neural networks for encryption. And you can also be basically resolution agnostic. Even if I increase the resolution of the image, the amount of time it takes does not change much. So you might be wondering, 200 seconds is still a lot to match just a pair of images, which can, in normal computation, can happen under less than a second. But this is on a CPU. So if you actually use a GPU, you can bring this down by another factor of 10, which is still computationally pretty heavy. But this is the price you have to pay for privacy with end-to-end encryption of everything at this point. So people have also demonstrated end-to-end encrypted large language models. There's a lot of papers on just in the last 1 year. So now you can take a Llama model, Llama 7B model, and you can do end-to-end encrypted inference. So you send a text prompt which is encrypted, all the computations happen encrypted, and you get an encrypted output at the end. So everything is secure. Nobody will be able to see what actually is the data that you have asked the chatbot or what the result of the chatbot also was. So these are still pretty slow at this point. The fastest right now is from this model here. It still takes around 40 seconds in order to obtain a result back once you type a prompt. That's not real time, unlike ChatGPT, which is pretty much instantaneous. But this is good progress that we have made over the last 10 years, where it was 1,000,000 times slower, but now maybe it's around 20 times slower. Unfortunately, these are all closed source implementations only, and they are not publicly available for us to use. So because they're all trying to build companies around this. So in my group, we are now actually trying to open source these things or develop an open source version of these encrypted LLMs right now. We can also actually do a secure retrieval augmented generation. We recently demonstrated this in the healthcare context. So typically, when you use a large language model, let's say a large language model over here, uh, you also need to provide it with some context. And this context can be obtained through retrieval from a database. So RAG, or retrieval augmented generation, is very common when using these types of large language models. But this retrieval augmented generation, you basically have a database of private information that you go search and you find relevant documents and you take those documents and send them to your LLM. In the healthcare context, these relevant documents could be electronic health records of a particular patient. And these are, of course, private, and you want to be able to protect their privacy and prevent unauthorized access to these electronic health records. So what we did is we built a system where, let's say you're a doctor, you query about a particular patient, and for that patient, you first go and retrieve all the documents that are relevant to that patient. And these documents are all completely encrypted. So you're retrieving encrypted documents. And you take these encrypted documents and the encrypted question, and then you send it to a large language model, which then gives you an encrypted result. And only the doctor will be able to see what the response is. So what this enables you to do now is I can, without worrying about anything about privacy, I can send encrypted data to any cloud service, any chatbot on the cloud, Gemini, ChatGPT, or Claude, and I can get back the response. And I can be sure that I can be guaranteed that the chatbot cannot see the patient data. So it's all encrypted, so it's all secure. So this is, you cannot do this right now. You cannot simply upload patient data to, let's say, ChatGPT without violating HIPAA constraints, unless ChatGPT is going to give you some legal guarantees that it's not going to use that data. Okay, so beyond chatbots, there is this iDash competition that happens every year. This is for genome analysis. This iDash competition, at least in the last 2 years, has been focused on using fully homomorphic encryption for doing this genome analysis. So the 2025 version of it just finished, and there were a few winners that were also announced where they do this DNA binding classification on completely encrypted genomic data. So it's a convolutional neural network, and you do this fully encrypted, and it's really, really fast and efficient. Very high performance. You don't lose any accuracy on this. So the story so far is that encryption is very useful from a privacy preservation point of view. However, using encryption has challenges, either from a software or a latency or a speed point of view, or from a usability point of view. But if you co-design the AI architectures and this encryption architectures, you can get a lot of efficiency out of these encrypted systems. You can be 10 times, 100 times more efficient than just blindly using encryption over standard AI architectures. But that's not the full story. There's a missing piece in this puzzle. So all of these encrypted computations happen on our computers, right? On a CPU, on a GPU. So we want this hardware also to be customized for encrypted operations. So people are now trying to build custom hardware for encrypted operations. So currently we use CPUs, which is a regular computer, or maybe a multi-core CPU, if you use a maybe powerful workstation. Or you can use a GPU, which is what people use for AI computations. Going from CPU to GPU will give you 100 times speed up. This is where we are right now. But if you design a custom custom hardware, a custom chip for encrypted computations, you can get 100 times more speed up. So there are a lot of companies trying to build these specialized chips for encrypted computations. So with that, I would like to maybe conclude this talk over here. So the key takeaways for this would be we can actually get a secure healthcare AI, which is end-to-end encrypted. It is achievable with fully homomorphic encryption today if you use specialized architectures, and if you are okay with not having to be real-time operations. So if you're okay with waiting for a little bit for the computation, for the heavy computations to go through, then you can actually deploy FHE today for healthcare AI applications. So there's already some of them out there, facial recognition, secure LLMs, genomic analysis, and I believe these applications will only exponentially grow in the future as the technology matures. As a next step, if you're interested in participating in this or knowing more about it, we actually have a tutorial. Last year at CVPR 2025. Here's the link for it. It has a lot of resources, a lot more technical details, and also open source code that you can go and use and play around with. There's a very nice community for discussing homomorphic encryption and its application. There's a Discord link over here. You can check this out. Or if you're interested in collaborating on this topic, please feel free to send me an email at vishnu@msu.edu. So with that, I'd like to take any questions that you may have. Thank you.
Thank you, Dr. Vishnu. That was an amazing presentation. If you don't mind, I'll hand it over to Dr. Wei Wang, who will help moderate this Q&A. Thank you.
Hello, thank you. Thank you for the wonderful talk. So we have one question submitted already. Given the noise growth limits, multiplicative depth, and necessitates bootstrapping to refresh ciphertext levels, what architecture or algorithmic strategies do you find the most promising for reducing bootstrapping overhead in FHE native neural networks, especially when targeting real-world biomedical dataset?
Yeah, so that's a really good question. That is actually what we did in the CryptoFace application. So the key idea is to reduce multiplicative depth, you want your neural network to be shallow, not deep. So this is contrary to common wisdom in standard neural networks. Right? In standard neural networks, you want your neural network to be as deep as possible. That's what makes it perform very good compared to wide networks. But for encryption, this has to be the reverse. You need shallow but wide neural networks. That's a way to reduce the number of bootstrapping operations to make this efficient. So, for example, you can see here, if I use a standard ResNet, I will need 30 or 40 different bootstrapping operations. That's too much. That's the reason why it's so slow. But if you make this shallow but parallel neural networks, then you only need 2 of these bootstrapping operations, and that significantly speeds up the computation. So this is at least the insight that we have been working with over the past couple of years. Shallow neural networks, maybe wide neural networks to reduce this computations.
Yeah, I also see that actually for the site phase, right? You have a somewhat more parameter space, right? Larger number of parameters. How do you think, like, what role this would play in
So the number of parameters, surprisingly, doesn't affect much in terms of computational speed. So the reason is in encrypted domain, you actually encrypt an entire vector of numbers. Let me quickly go back and show you that. You don't encrypt single number at a time. You encrypt an entire vector. So even if I have a lot of parameters, if I can fit all of them in one encrypted vector, I'm still doing only one computation. So the number of parameters doesn't affect the speed or latency. Of course, it will affect the amount of storage that you need on the disk if you're storing it on the disk, or GPU or CPU RAM that you use. Yeah.
Thank you. The second question regarding ways to increase efficiency when performing computations on encrypted data. What do you think are the biggest obstacles to overcome now?
So there are a couple of things. Actually, there's three things I can think of. So one is the core encrypted computations need to be made faster. So how do you add numbers in encryption? How do you multiply them? Bootstrapping. So there are people trying to speed that up. So that's the first thing. The second thing is designing custom neural networks for FHE rather than taking standard neural networks. So that's the second way in which you can significantly speed things up. The third is use a custom hardware. Instead of a GPU or a CPU, you use a custom chip that is designed for FHE computations. I think with these three things, we will be able to match or make encrypted AI systems as quick as standard AI systems. Right now, progress is happening on all three fronts: better encrypted operations, better software, better neural network, and better hardware. But they all haven't come together yet fully. But once they do in the next 1-2 years, then we will see this really be very efficient. You can even use them for real-time systems. I hope that helps.
Yeah, thank you. So there's a related question. What do you think is the biggest bottleneck to a real-world clinical deployment of encrypted ML today?
That's a tough one.
Yeah.
Sorry to put you on the spot.
No. So I think the trade-off is between computation and accuracy. So if we want really high performance or very high accuracy healthcare AI models deployed in the real world, these models are really huge, right? Lots of parameters. You want to process high resolution images and things like that. But those are precisely what makes this whole encrypted computation slow. So it's a trade-off that you have to make between computation and accuracy. So we are making progress on the computation aspect, both, as I said, from hardware, neural network, and also from the software side. So I think if we wait for, we have to just give it time, and then it'll start becoming more practically relevant. But certainly, you can already use it today if you are willing to, let's say, wait for 5 minutes or 10 minutes for your image to be processed or for your computation to be processed in the healthcare. But if you want a real time, you cannot use it today. So I hope that question sufficiently addressed, I would say.
Thank you so much. I think we're at the hour. Thank you so much for the fantastic presentation.
Thank you.
Thank you all. Thanks for the opportunity. Thank you.
We've all learned so much, Dr. Boddeti. We look forward to have more conversations and to learn more from you. Jack, would you like to give a brief mention of our lecture series for next week while we're wrapping up this session?
Yeah. So our lecture series for next week will feature a lecture from Teresa Wu. She will be talking about some very important things in um, novel technologies for AI. But I did want to say something real quick about Dr. Vishnu. I want to just reiterate how awesome this lecture was, and the biggest strength of the educational modules that Vishnu offers is really it really comes from remarkable scholars and investigators like yourself who share their expertise with us. And our program is only possible because pioneers like yourself are willing to deep dive and tell us all about it in really clear and understandable ways, so the community consortium can also benefit from your work. And that's just awesome. And we're grateful that you were able to help us with that. We will have 3 more lectures planned. Um, please stay tuned.
Okay, all right. Thank you very much. Thanks, everyone.